Hello, hello, hello. My name is Joseph Milko of Technically Speaking at Source Allies. This year, once again, we are sponsoring Advent of Code. Now, Ben already did an amazing video for day 3. Gray did a great one for day 7. I happen to do one for day 14. If you haven't seen any of those, you're missing out. Today, though, I am doing Advent of Code day 20. Now, just so I can share this live experience with you, I have abstained from doing it just as they release. It's usually when I do so. It has been nice to go to sleep at an earlier time, though, so I will appreciate that. Without further ado, I have my code here. VS Code is running, Quark is running. We are ready to go, and we're going to jump in straight into the problem and see what we have. Okay, we have day 20. It's a grid. So we're going to be pathfinding somewhere, finding ourselves a path. So let's take that input, put it right there for our test case. Map consists of a track. Yep, so dots are traversable. S means you can start. End is the E. Walls are hashtag, octothorpe, pound signs. We can cheat. That's always a good sign. How many cheats would you save at least 100 picoseconds? Okay, so they don't really have the answer to our sample here of our example, so we have to read it. Okay, map of a racetrack. This is it. Okay, so it's not a maze, it's a racetrack. Racetracks usually have a one route only through them. Each movement costs a picosecond. You can disable collision for 2 picoseconds, pass through walls. Okay. So we can cheat at that position. So go through the wall that's at 1 position, end up at 2 instead of going down, across, and then up. Okay, I understand. Or you could cheat at a different position. Okay, so you can only cheat once. So we are looking to find out how many positions could you cheat, and it would be worth the cheat, basically. And their definition of worth the cheat is 100 picoseconds. Okay, so I'm seeing this already where we need to take this, we need to parse out the starting and ending location, and then we just need to run a basic Dijkstra. No, we don't even need Dijkstra. There are no weights. Every movement costs 1, and by the definition of a racetrack, you won't have branches, so it's just going to be following the yellow brick road all the way home. So this is just going to be a breadth first search, just following the traversal. And then I think for the actual shortcutting, if I'm here, then I can shortcut to here because it is within 2 distance to me, because I can turn visible for 2 distances, and I can cheat to anywhere I want. I would want to cheat here because it is a position with a higher time. So let's say it took me 10 seconds to get here, it takes me 20 seconds to get here. If I go straight from here to here, it now takes me 12 seconds to get here. Okay, I don't know how I'm going to do that, but that's what we're going to want to do. So we're going to turn this into a lovely world. Let me turn off Copilot. Very sorry, very, very sorry. Okay, I cheated a little bit on how to split this, though I have done this so many times. That's not really a spoiler. So const world equals data split on the new line characters, giving us an array of strings, and for each of these, we're going to turn the string into an array, so that way I can manipulate it as I need, which gives us a row that looks like, not worker data, which gives us this, an array of arrays that I can manipulate as I see fit. Now I need to find the start and type locations. So type location equals rows number, column number, and this is what I'm going to go with. I prefer row and column because you can't really mix up row and column like you can X and Y. So let start location equals, and we'll use the classic -1 for not found yet, though this shouldn't really be a concern. Let's do the same thing for end. May not specify known. Oh, I've spelled it out fully. Let's save us some characters and not do that. Now let's traverse through the world. R equals 0, R less than world.length, R++. So for every single row, we're going to traverse through it. Of course, for every row, we're going to iterate through every column. And then we're going to get the character at that column. So const car equals world row column. And what do we want to do? We're looking for the S's and we're looking for the E's. So let's say if character equals S, we did it, start equals our current row and column. And just to make our traversal later easier, because we're going to be like, hey, can we go to this place? We're going to replace the start and end on our grid with dots. So that way I don't have to add if this, if a dot, or an S, or an E. I can just say if it's a dot. So world row column, back to a dot. We're going to do the exact same thing for our end. Capital E, END. And now we can test if this works right now. We should get a start of 0, 1, 2, 3, 3, 1. So let's see if we got a start of 3, 1. Boom, we got a start of 3, 1. We should have an end of 0, 1, 2, 3, 4, 5, 6, 7, 7 something. Boom, our start and end code is working. Now, we need to actually start following our path. So we're going to keep this simple, thankfully, because I recognize it's a racetrack, not a maze, so there's not going to be any branching. We're not going to have to follow different timelines of what if we go here, what if we turn right, what if we turn left. We're just going to keep going until we reach the end. So all I'll need to do is keep track of effectively a queue of all the places I'm going to be going to, and we'll start with start. Of course, I wanted to keep track of how long it took me to get to every position, so I'll need a map of const, let's call it times, and this hash map, I'm just going to make it really easy to follow along with. So this is the from location, and then the value, of course, is just the number, how long it took me to get there. Now, what we want there is an encoded location, not just a location, because welcome to JavaScript, you can't just use anything as a key. Even if I was using a map, the referencing would kill me. So we're just going to encode location, and we'll just return it as location r plus vertical pipe plus location.column. 15 different ways of doing this. This works the best. So now we can, and we're going to save this for later, encoded start equals encode location start. So I got a feeling we're going to need to do this a few more times, or at least reference these a few more times. So we are starting at the encoded start position. Our loop is just going to keep running until our queue is empty. So while our queue.length, let's put a break here so my computer does not die. One thing I forgot, we need to initialize our times with how long it took us to get to the start, which is 0. It took us no time at all to get to the start. So times encoded start equals 0. Hey, look at that. The thing's already Woo, where did I put those? I was saying that variable is already doing a good job getting reused. So once we have our queue, we're going to iterate through it, and we're just going to take the current out of our queue, and we can do some efficiencies here. Let's get it working before we make it all pretty and fancy and fast. And we wouldn't need to, but let's do it just in case. So if we have entered the end, so we made it. Congratulations, we finished the race. Encoded end, then let's break out of here, just to be super safe. Now, sometimes I would make an adjacency map of the originating points and their destinations, but given we don't have weights and for other reasons, I think it'll be quicker to just do it inline here, which is why I haven't created anything above. Which means we're going to do our traversal here for every possible offset position, all 4 cardinal ones, north, south, east, and west. We're going to see if we can go there. So let's say cardinal directions, and we're just going to encode the offsets for north, south, east, and west. So this one, south, east, and west, or west and east, whatever that is. Cardinal directions, we have them all here. And now we want to go through each one. So for the row offset and column offset of cardinal directions, now what we get to do is we need to figure out where that new coordinate is. So the new row, the new column equals the row plus the row offset, column plus the column offset. But of course, we don't have row and column because what we're current is an encoded location. So, hey, don't worry, TypeScript, that's a real thing. So let's pull row and column out of this by decoding location, which we will write right now. But we won't run it here because don't need the row and column. If we don't need the row and column, we're going to end early. So another cool function, encode location, decode location. You're given a coded location, which is a string. You return a location, so let's do that parsing. Row and column, you take the encoded location, you split it. Nope. Encode id location. Thanks, VS Code. And you split it by that vertical bar. Gives you an array of characters. You take each of those, turn them into a number of the old number constructor. As you structure it, because we know there is going to be two. And then I use the shorthand object syntax to return row and column as the key and value. So we did all that. Now we have our decoded location, which is our row and our column, which allows us to calculate our neighbor's row and our neighbor's column. Now, the thing about our neighbors is we can't go to all of our neighbors. We can only go to a neighbor that has a dot. So this is why converting those S's and N's to dots helped out. So if world, and let's put this in a variable cost. We don't need it in a variable, actually. I was thinking if we needed to use this earlier or again, and we don't. If it's not equal a dot, as in we cannot travel there, then let's not look at this direction anymore. It's useless. Optional chaining in case we go below or above our maximum row count. The rest will evaluate to undefined just perfectly. So now we have our neighbor. We need them actually encoded because we need to get their previous times, new times, and stuff like that. So that'll be our neighbor equals encode location, our neighbor row column, neighbor column, and we might not actually need to if this is a straight line. Let's just put it in there. So times neighbor equals the current time plus 1. What's my current time? My current time is times current plus 1 is plus 1. So congratulations, we went to you, and we're going to say we're going to go to our neighbor. Now, if my assumptions are correct, this is a racetrack, it's a straight line, well, it's a single line. I should be able to brake once I do find a direction. So this is an optimization. It's also a check of my assumptions. So we've done that. Hopefully we're running a lot of times. Ooh, we have ran out of computer. Okay. So we've done something infinite, very bad of us. Now we get to look into why. So here's the problem. So let's take these two, for example. I went from here to here, and then I was like, oh, look at my neighbor. I'm going to go back there. So we do actually need to do some logic for never visiting the same place again. I didn't go with a set because I went with this. So let's say new time equals times current plus 1 cost per neighbor. I can spell the word neighbor. Neighbor time equals times neighbor or infinity. Gotta watch out for that. If new time less than neighbor time, basically it's effectively saying this is the first time we've seen you. What's wrong? Neighbor time, not neighbor. Then what we're going to do is these three lines right here. Boop, boop, boop. Let's bring the brake also. Okay, slight change. Let's see if that works. Okay, it did not infinite loop us. So we made it as expected. All of these are just increments. 84. How long does it take to go through this maze? Do I see 84? Okay, so that means we're traversing the maze correctly, which wasn't the real hard part. Now it's time to cheat, right? Okay, so my theory for cheating again, if I am here and I look at every position that is 2 away from me, then I'll find ones that are in the future. That's kind of pointless going on a straight line. Let's not worry about that. It's going to be inefficient, but it's going to work. So I'll find this one that is in the future, and if I add my 2 to it, if it takes me 10 to get here and 20 to get here, congratulations, it now only takes me 12 to get here, and I save distance. If that's 100 distance, we'll find out. So that is basically traversing every position and every other position. Technically, it's traversing every position and every position that is 2 away from it. Let's just see if this works before we go for the efficient math. So this is kind of like an A and B. So this is row column. Yeah, I'm going to steal this, actually. And yeah, this isn't going to be pretty, but it's going to work. That's actually what we're trying to see. We're going to hope it works. Let's rename this to AR. Let's rename this to BC. And then so we can make another copy of this, so we can say BR and BC. Let me get back in there. BR, BC. I hope I've accidentally named this one the wrong thing. This is supposed to be AC. Okay, so we have the row and column for our A position and the row and column for our B position. Now that we have both of those, we can do a little bit of safety stuff. We're only going from dots to dots, so if world AC, well, AR, AC, not equal a dot, let's be strict equality, continue, move on with your life. Same thing for the B's. Boom, we've done that. If you're not, things we can actually navigate between, we don't want to look at you. Another good reason that I replace my start and end with dots, so I can do that. Now, what we want to do is get the distance and make sure that it's 2? Less than or equal to 2. Yes, less than or equal to 2. So we need to calculate the distance. I'm not sure which one this is. Manhattan, taxi cab, Euclidean, all that stuff. I'm just going to do my classic one. AR minus BR plus the absolute of AC minus BC. Yes, add the differences between the rows and the columns. Now, if that distance is greater than 2, then we continue. We don't care about you. So, you're too far away. That's going to eliminate the majority of them, honestly. And now we need to get the distance or the time that it took to get there and the time it took to get the one we're considering. So let's do that. So time to A, that's going to be times, I mean the encoded location. So encode location R, AR, B, no, C, AC. Really hope I don't need these later. Time to B, BR, BC. We can do some optimization moving this up in the loop, but we're following it through logically. So now we have our saved time, which is the largest subtracted the smallest, so times to B, time to B, I know how to spell, minus time to A. So that's how much we saved. If we haven't saved any, or if we've saved negative because we're going backward, again, we don't want to do this. So if saved less than 0, continue. Okay, we got to be getting close to something that's actually good. So we have saved some time. Is it enough time? We don't know the answer for the real one, but we are given this. We're given the number of cheats for every second. So let's do that. This is going to be our only way to validate. So save counts equals a new thing, record, string, and they're technically numbers, who cares? So if we have saved this much, we want to count how many times we've saved by 2, for example. So if not saved in saved counts, save, initialize it to 0, as always. Otherwise, we're going to go ahead and, my hands are all over the keyboard today, but as always, not otherwise, we're always just going to increment save counts of however much you just saved by 1. So if we get something that looks like this, we've done it. We just need to add the conditional for the 100. So save counts. Man, oh no. Okay, that's not what we wanted. So, which means one of these aren't a number. So BR, BC, AR, AC. So time to A. Lots of undefined. Oh no. Which means we've never been to this position. I did it. I inverted these. So I was looking at the time between one hashtag and another hashtag. I've never been to a hashtag, therefore the time to that position was undefined. But if we flip this around, look at that, we're comparing actual dots. 0, 1, 2, 3, blah, blah, blah. That's a lot of numbers. That is also not what we are looking for. Okay, so we have 85 zeros, 84 ones. Okay, so we have a lot of them here. We have 184. So you know what you're doing? You're teleporting to the end. You can't do that. That's illegal. It is just the day of typos. We don't want the arc sign of a number. Jeez Louise. Okay, let's try it again. This is looking better. So we have 85 zeros. Hey, if we save none, let's not look at you at all. If we save one, okay, that's weird. You're literally just moving forward. There's some room to improve this. Yeah, let's do less than or equal to 1, because that's not a valid save. Okay, so there are 83 twos. No, it says there are only 14 fours, 6s, 2, 4, 2, 3, 2, 4, 2, 3, a bunch of 1s up to 66. So, you know what I'm seeing there? I'm seeing an off by 2 error. And 2 is the new cost it takes to actually move here. You don't just teleport from here to here. You move or you drive from here to here, which costs you the distance that you are. So it costs you distance, so I have to math it out of here somewhere. So we have the time to A. So let's make it easier. Cost new time to B. It is the time to A plus the distance. There we go. Now we subtract this one. I think it's the right order. Math. Yeah, let's just see about it. 2 14s, well, 14 twos, 14 fours, 2, 4, 2, 3, 2, 4, 2, 3, 6, 8, 10, 12, 6, 8, 10, 12, and a bunch of 1s all the way up to 64, and a bunch of 1s all the way up to 64, specifically 5 1s, 20, 36, 38, 40, 20, 36. Okay, I think I got it. Now we just have to add the logic for the hundreds, which again, we don't have an example for. Let good to cheat. I don't know what the name of this is. So if saved at least 100 picoseconds. I think that's greater than 100. Probably going to get it off by 1. Good to cheat. Yay. Let's return good to cheat. We actually can, though. I just realized use this by just adding up all these. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. This and this and this. It's completely somewhere in the 40s. 40 something? What are we actually getting here? 0 is not equal to 40. Hey, it's not returning because it's 100 in this case. Cheat minimum, it's a number. There we go. We can set this to 0 so that way we can actually get some understanding here. If it's greater than the cheat minimum, then we're good to cheat. Yay. 0. 44. I'm going to assume I just didn't count it very well. And it was actually 44. Now we got a 0 because I haven't put my input in. Let's do that. Get that in. Hopefully it's good. Make a change. Uh-oh. That's not good. Oh, that's okay. That's okay. That's a number. So it ran a bit long. This is an awfully big maze, though, and I'm using the least efficient try and cheat algorithm in the universe, so that's understandable. Oh, that's not the right answer. Oh, no. Okay, let's head on back. We will figure this out. So, 1173 is not the right answer. Is it this? It said at least 100 picoseconds. 1197. I don't know. We won't be able to find out for like 30 more seconds, I think. 26 more seconds. Okay, let's prepare for part 2, though, conceptually. This is gross. This is absolutely the grossest. And I'm only considering things that are in front of my path. So I shouldn't be traversing over the entire world. I should be traversing over my path and only going over things that I have that are in my path. So if I'm at a previous position in my path, I should only look at positions that are next in my path. I've explained that horribly, but let's solve one thing at a time. Boom, okay, I was off by 1. So let's do what I just said. Well, maybe we don't need to do what I just said. Ooh, they can cheat by 20 picoseconds. Oh no. Okay, so we need to get that working. Let's go for that. New terminal. No, just give me new terminal, please. Thank you. Because I got a feeling this ain't gonna work, because we saw how slow Wallaby already was. You are giving me more numbers here, but you're giving me 50s, and I'm not gonna go through that and add them all up if I have working code. So solve 2 is just returning solve 1, but we'll need another parameter to make it go gooder, or go further. So let's say 20, and that's going to be a parameter for how far you can cheat. So cheat distance, there we go. So cheat distance, that's a cool variable we're going to make up. We're going to put it right here. Cheat distance is a number. We're going to have to initialize it for the rest of them, because these are all angry. Your cheat distance is 2, don't you worry about it. Let's remove, nope, go back. Remove that, because my Quokka is running slow. Expected 0 to equal true. Yeah, we don't have an example. I could do math here. We're not going to do math here. We're just going to go for it. So, it's running. Let's look at that Let's take this number. Let's not look at this optimization. That's a big looking number. Boom. Okay. So, we got it. Optimization be darned. It was good enough. So, very quick run through what we did. We parsed out the start and the ending. We got rid of the start and ending characters for traversal. We kept track of how long it took us to get to each point in our racetrack. We then simply followed the racetrack. It looks a little gnarly here, but it's because I'll take this credit on this one. I did not think of keeping track of everywhere I visited. Therefore, I just used this both as a how long did it take me to get here and a have I been here data structure. It works. Then I did the least efficient thing in the universe, and I looked at every position compared to every other position. Of course, I only looked at the dots, so places the car could have been. And I was like, hey, are you within cheating distance? Can I cheat to you? Can I activate my power up and I drive to your position? If no, ignore it. Otherwise, let's say I did cheat and turn on my invisibility or whatever, and I drove to you, how much time would I save? Would I save 0 to nothing? Would I save negative time because you were literally behind me? Get rid of them. Then we count this, which does nothing for us. This was just debugging for my eyeballs. And we say, okay, if we've saved enough that we think is worth it, then we're going to say we found another place we could cheat. And that changed on all of them. Well, it changed on one of them. Our 100 still became how many picoseconds we would want at minimum to cheat by. Like I said, the optimization here would be keeping track of where I've been and only look at future possible positions. That would probably make it run instantaneously, but I don't want to run this over this for too long, so we will call it there. Again, thank you for coming along with this adventure, helping programs figure out which maps are the best to cheat on for Advent of Code Day 20. My favorite part is seeing all the different solutions and all the different approaches to this, but that is the end. So, this has been Joseph Milliken with Source Allies. Got a topic you want to hear about, or you got an insight or a solution for this particular challenge, feel free to drop it in the comments right below. If you're just a touch curious about us, I'm inviting you to come on over to our corner of the internet at sourceallies.com to see what we're all about.